Hello, guys, and welcome to another daily Leetcode challenge. I again lost my streak, but we'll start again from zero, I guess. Okay, so let's see. Question 2492, minimum score of a path between two cities. Minimum score of a path between two cities. You are given a positive integer n representing n cities, numbered from 1 to n. You're also given a 2D array roads, where the road of element I, where each element is essentially a 3-element subarray consisting of A, B, and distance, indicates that there's a bidirectional road between cities A and B, with a distance equal to distance. The city's graph is not necessarily connected. Okay, so before we dive deeper in, I'm imagining just a collection of cities and roads between those cities, the representation of which can be done in the 2D array that they're proposing, where the outmost dimension is just the number of connections, and the arrays inside of that outmost dimension is just the structured representation of A, B, and distance. Okay, so the score of a path between two cities is defined as the minimum distance of a road in this path. Okay, so we're supposed to return the minimum score of a path between two cities, and it's asking us that the score of a path between two cities is defined as the minimum distance of a road in this path. The minimum distance of a road in this path. So, okay, return the minimum possible score of a path between cities 1 and n. Return the minimum possible score of a path between cities 1 and n. Okay, so 1 and n are just the beginning and the end cities, and we're supposed to return the minimum path. Well, this would be 7. This would be 11. So is this like a find a minimum path question in which we would use the extra? Let's see. Note, a path is a sequence of roads between two cities. A path is a sequence of roads between two cities. That all makes sense. It is allowed for a path to contain the same road multiple times. Why would that ever happen? Okay, I'm reading all of this, and it's right away, this doesn't entirely make sense. Let's see if we can make some more sense later. The test case are generated such as that there is at least one path between 1 and n. Okay, so although it could potentially be disjoint, cities are not necessarily connected. At least there is a path between 1 and n. Okay, so in the example 1, we're given that there's 4 nodes, and the roads between those nodes are 129, 129, 236, 236, 245, 245, 147, 147. Okay, the output is 5. Wasn't it 7? Explanation: the path from city 1 to 4 with a minimum score is 1, 2, 4, 1, 2, 4. The score of this path is minimum of 9 and 5. Oh, they're defining... Okay, so they're defining score as not just the length of a path. The path is actually the minimum road. Okay, I see. So imagine that we have to travel from New York to San Francisco to LA. The total distance from New York to LA is obviously from New York to San Francisco to LA, but the smallest path is just going to be, or the score of that path is actually just going to be the distance between San Francisco and LA. Okay, I see. Um, so first, I'm guessing that trying to think of this, there's a couple of different approaches to finding the minimum path. For example, there's a diextra that we've previously solved. I'm thinking if that could be modified somehow to facilitate finding us the smallest score path. But what about this example? Let's see. Another thing confused me here, which is that um, a one thing that very stood out and probably stood out to you too is that the same road can appear in the path multiple times. I'm thinking, how are you going to ever repeat a road and a path multiple times if you're just trying to get to the thing as fast as possible, to the destination as fast as possible. So maybe this shines some answers. Same four cities given, and the roads here are now 1 to 2, which is a 2, 1, 3, 4, 1, 3, 4, and 3, 4, 7. So from 1 to 4, the shortest path should be 4, but the output is 2. Okay, so that's counterintuitive, but that kind of makes sense because if they're saying that the road in the shortest score path can repeat multiple times, well, what if we travel from 1 to 2, then back to 1, to 3, and to 4? Then the output is actually 2. Okay, so now so now it almost seems like we can just look through all of the distances. Let's look through all of the distances in the road and just pick out the smallest one, right? Would that work? Let's see. How would I do this? I can say m is equal to some very big number. Let's see, what's the constraint here? Distance is one with 4 zeros, 1, 2, 3, 4. And we will just say that for road and roads, if we'll just say m is equal to min of m and road 2, return m. And that should be it. See, this would only not work. Is there anything here about the paths being... Oh, didn't they say that the graph doesn't have to be connected? So if the graph is not connected, and if there, besides this graph in which the path will definitely lay, if there is another subgraph here that's not connected, then this approach here wouldn't work properly. So, okay, for anything that's okay, I have another proposition then. We know of a way to find all subgraphs pretty easily with a technique called union find. What if for each cluster of graphs we define the minimum path of that cluster? So this would be just a tiny modification to union find, but that would allow us to consistently store the minimum path for each of the graphs. And then when we unionize two graphs that potentially were previously disconnected, then the way that we define which um, minimum will actually win is simply by finding the root of the first subgraph and then the root of the second and picking out the minimum. Let me show you what I'm talking about. For those of you who don't know, union find kind of looks like the root of maybe like 2 or 3 trees. This is what I'm proposing. Let's say that we have the distance paths will be the same. So this is what it sort of looks like. Um, maybe this has another one here. Basically, what I'm trying to indicate here is that there's no it all it almost looks like a tree, but it has absolutely no structure. The only thing that unites all of these um, the only thing that unites all of these roots or minimums is that they have a common root, and that is because when you have another sort of similar graph here, or another portion of the union find that's possibly a bit disconnected, you could end up with something like this, say 5. So imagine that the union find is currently, we've added links between 3 and 4, then 4 and 5, then 3 and 4, then 4 and 0, and then 2 and 0. And we have not yet found the links between any of these nodes in these 2 different clusters. So what happens when you're unionizing then, let's see, a 0 and an 8? Or let's unionize a 3 and an 8. Well, here's how union find works. We have an array, and we have a function called find, and another called union. This is our data structure that's actually going to store this whole setup. Find is going to, given a certain node, it's always going to bring you to the most top element, and it's going to return that element here. So for example, if I was to find the element 3, well, I would, well, let's see, let's call this 2, because otherwise it's repeating, and let's call this, I don't know, is 6 not here yet? Yeah, 6 isn't here yet. 7, 8, okay, this way I'm not repeating anything. Let's call this 10, 19, 10. So just a little check. What would I do if I was to find the number 10? This function would return to me 1. If I was to find number 10 or number 8 or number 7 or number 1, I would always find 1. If I was to find any number 4, 3, 2, 5, 6, or 0, I would always get 0. This is how it works. Let's see. First, I outline the number of cities that I'm going to be using. So I'm going to call this N. n. Oh, and actually, since it's 1 indexed, I'm going to, oh, since it's 1 indexed, and at the beginning I want all basically, at the beginning, before I merge any of these, I want there to be this many 4, 5, 6, 7, 8, 10. I want there to be each node basically being its own subgraph. Okay, each node being its own subgraph. So what that means is that I'm going to say for I in range, let's see, it's 1 index, so it's going to be n plus 1. I plus 1. Well, let's just see that first of all I'm getting this correct. I'm printing 1, 2, 3, 4, 5, 0 index. Okay, perfect. I did that correctly. I just wanted to make sure. How would we implement find? Well, find takes in a value, and if the value is equal to union find value, so if the parent, and union find simply just stores for each value, index of it representing the value in that index is going to be the parent. So if currently index, oh, no, I did this wrong. I have to have a 0 here as well, right? Because this is how it's supposed to be. I'm supposed to have 1, 2, 0, 1, 2, 3, 4, 5. Let me run this again and show you what I mean. Each element, oops, there we go. So we only have 4 cities. Each element in the array will currently be pointing to a parent of itself. The index 0 has a parent of 0 itself. The index of 1 has a parent of 1. What we're going to be doing here then is saying that if value that we're being passed, which is actually just the indx, if indx is equal to I'm going to call it indx, if index is equal to index, then we simply return ourselves. Else, and this doesn't have to be in an else statement because this is also going to be executed, I'm going to say that while indx does not equal uf dx, indx is equal to uf indx, and then indx. So what this find looks like here is, let's look at 3. Is 3's parent 3? No. Then I'm going to start looking at its parent, 4. Is 4's parent 4? No. Then I'm going to look at 0. Is 0's parent 0? Yes. Why is it? Because this is the top, this is the vertex, and it's going to be pointing to itself. So there we go, we have find defined. Now how do we do union? Union is usually of 2 elements, so city 1 and city 2. We're going to find the parent of 1, which is going to be find C1, and we're going to find parent 2, find C2. Okay, so now that we found both of our parents, we found these 2 pinnacles. Well, now we have to unionize them. Now we have to say that 1 is, and I cannot copy this right here, but Or maybe I can. Oops. No, I'm copying this parent, these two values, and I'm saying that this will now be pointing into here. So how do I do this? If I could just shift this one like here. Basically, not only 6, 4, but also 1 will be pointing at 0. So it's as if now it only has one element if we were to join 0 and 1. But keep in mind that we could have joined 2 and 10 and we would have gotten the same result. Why? Because first we're finding 0, then we're finding 1, and then we're going to perform the same union. But the only thing here is that we have to perform the union smartly. Because the union is going to be representing another minimum value, which I have not done yet, let's call this the very big number times n plus 1, actually. Because it's been 1 indexed, and if we get a number like something like 10, then it's going to be in the 10th element. Anyway, so the minimum is going to store the minimum of each of the pinnacles. And because each of the pinnacle is at the beginning just itself, I'm going to start it with the very big number. And when we have a union between two, I'm just going to replace this minimums array with whatever the distance is. So either 6 or whatever, we'll see. Okay, so for that, I actually would probably need the distance as well. And here I'm going to say min distance is just the min of distance. Oh, and then I also need the minimum of the previous two pinnacles. So m p1 and m p2. Now I have the minimum distance, and now I have to figure out which of these pinnacles are actually going to become the parent, right? So if, would this be like this? If P1 is smaller than M P2, then what does that mean? If it's smaller, then P1 has to become the parent. If P1 has to become the parent, then simply UF P2 now no longer is pointing to itself, but it used to. Now it's pointing to P2, P1, sorry. And then also we're going to update the M of P1 with the min distance. The min distance could have been previously of P2. And else we just do the same thing. UF P2, we just do the opposite. P2 M P2 is min dist. At the end result, what is my pinnacle that I'm actually going to return? Well, it doesn't matter, right? I can just find either 1 or n. So I can simply say m and return the parent of either 1 or 4 because I know that those are in the path. So m find 1. Awesome. Completely wrong. Oh, well, I actually have to populate union find. So let's populate for road in roads. I'm going to say union and road, the first element, road, Second and the distance, 2. Okay. Oh, sweet. So, whoa. 96. Are there any better solutions? Not union find. Guys, have we just stumble on? No. Union find. Okay, so same thing. I'm not gonna rewrite it because 96. I'm happy with 96. Okay, so I guess just we're back on that union find train. Uh, yeah, yeah. Feel free to use this. I'm going to get rid of this drawing. Hopefully, it kind of frees up some of that real estate. No, 97. Okay, yeah. So, guys, thank you for watching. I feel very, very comfortable with union find, and think how I think that when you see something disjoint, you immediately can think union find because that's essentially the O1 in time complexity solution to finding all the disjoint sets. So if we're starting to getting these questions, I'm sure that we're going to get more. So yep, thanks for watching, and I'll see you later. Bye.